Today we will discuss the differential form of energy equation, and we will derive the pressure energy relation. So, we will I will start from where we have left in the last class. So, we have seen this equation where Q is the total heat supplied, Ws is the shaft work, E is the internal energy, and V is the volume, which we have reduced to this form. Out minus in for one exit and one entry. Okay. So, that is a reduced form 1D equation of that. We will apply this to infinitesimally small control volume and derive the differential form. Where Q here, Q is 1 by m dot dq by dt, and Ws is 1 by m dot dws by dt. Okay. So, equation 1 apply to infinitesimally small control volume, and that is how we derived the differential form of any governing equation, any kind of equation. So, I have a control volume which is infinitesimally small. The dimension is given, the characteristic dimension is dx. I have an inlet, outlet. This derivation is also true for third dimension as long as we take the third dimension equation. So, let us stick to 1D equation. So, at the inlet the density is given by rho, pressure P, velocity V, and what are the quantity? Internal energy U, okay, and the total energy small e. At the exit it is rho plus d rho, P plus dP, B plus dP, U plus du, and E plus dE. Okay. So, we write this equation Q Ws plus E plus PV in out minus E plus PV in Ws plus E. We substitute the out quantities, out are these quantities. So, it is, so instead of E plus dE E plus dE plus P plus dP multiplied by V plus dV, which is the out quantity, okay, minus the in quantity, which is E plus PV. Pardon? Ws, I expand this, E and E cancels out, or E we will expand it as U plus du plus V plus dV the whole square by 2 plus G Z plus dz, okay, plus this quantity, which is pressure and volume, P plus dP multiplied by V plus dV minus U plus V square by 2 plus Gz plus P V. Okay. So Q equals Ws. So this U and this U cancels out. So what's left is du. So this V square and V square cancels out. So you have 2 V dV by 2 plus dV the whole square by 4 plus G dz. So PV cancels out. You have V dP plus P dV and the higher order term. Okay. So I have expanded this and cancelled out all these terms. Yeah, there is, this is correct. dV square by 2, yes, this is dV square by 2. Okay. Neglect your higher order terms. So this goes and this goes. So you are left with Q equals Ws plus du plus dV square by 2 plus G dz plus this is d of PV. So that's nothing but Ws plus dH plus d v square by 2 plus g dz. So, this is something that is applied to this infinitesimally small volume, and even if it is third dimension, you just consider this differential as the third dimension. Here the q and ds is also the small differential, because what is going in as q is dq for a small differential volume, and the work that is obtained is ws. So, ideally this should be dq and ds. So, this would be dq and ds, that would complete the differential form. Okay. So, this is the energy equation in the differential form. Okay. Now, we will proceed further. V dP. So, this is one of the so called Gibbs equation. So, dH we substitute from this equation. So, dH from equation 2, H is dq minus ws minus v square by 2 minus gz from equation 2, which is your energy equation. Okay. Now, TdS contains two components. Two components are TdS irreversible plus TdS reversible. Okay. And from the second law, we have T ds reversible equals Q, the heat input. Okay. So, substitute these equations, say 3 and 4 in the first equation. So, let us say that is your first equation. Okay. So, this is T ds reversible plus T ds irreversible equals dq minus dws minus dv square by 2 minus g dz. Minus v dp, which I replace it as dp by rho. Okay. So, now dq is this T irreversible. So, I cancel out this term. So, my So, I cancel out dq with the irreversible entropy change. So, what is left here is dP by rho plus G dz plus dV square by 2 plus dWs plus T ds irreversible equals 0. Okay. Even though Q is explicitly absent, this is also valid for process with Q, because we did not assume Q to be absent here, we just cancelled out Q with the reversible entropy change. Okay. So, if you have a system with Q input, this equation is still valid. Okay. And this equation is, where I rewrite this here, zero. So, if shaft work is 0, dWs is 0, and if no losses, implying d irreversible is 0. So, entropy change due to irreversible process is 0. I lose these two terms in the end. What is left is dP by rho plus G dz plus dV square by 2 equals 0, which is your Euler equation. Okay, 1D Euler equation. So, the differential form of energy equation, from the differential form of energy equation you get these equations. So, if the process is isothermal, so if the process is I have PV equals constant, P volume is constant, or P by rho equals constant. Okay. So, for process 1 to 2, process from state 1 to 2, you integrate this equation to get so from process 1 to 2, dP by rho plus integral G dz 1 to 2 plus integral dV square by 2 1 to 2 equals some constant, where you substitute instead of rho, I substitute dP by P into some constant C plus this. So, instead, if the process is adiabatic, PV power gamma equals constant, you substitute the appropriate value of P substitute the value of rho in terms of P with this equation and get a different form of equation. Okay. So, these are the energy equations for isothermal and adiabatic process. Okay. For an incompressible flow, the density is constant, so it is convenient to take it out and you can integrate and get the Bernoulli's equation. Okay. So, this constant is a different constant from this constant. So, this is C0, this again is a different constant. So, this would be C1 and you integrate this equation with the appropriate value of P. Okay. So, what we have done today is the differential form of the energy equation, and from which we have derived the pressure energy relation, and we have seen some special cases. We will be using this equation further in our gas dynamics course. Okay. Okay. So, that is for the day. Thank you.